Okay, so our speaker today is Ulrich Pennig, and his title you can see there, Topological Invariants for G-kernels and group actions. Please, Uli, go ahead.
Okay, thank you very much. Thank you for the invitation and for the opportunity to give this talk. This is a talk about a project that I started with Sergio Giron Pacheco and Masaki Izumi. And the second half is part with my, or the last part is joint work with my PhD student Valerio Bianchi. And it's a project about topological invariants for G-kernels and group actions. So I think I should start maybe explaining what I mean by a G-kernel. So throughout the talk, G will be a countable discrete group. And I have a unital C star algebra A, and then we all know what an action of the group on the C star algebra A is. It's just a homomorphism from G to the star automorphisms of A, like this. And then there's various ways of relaxing this notion. And one of them are these G-kernels. So a G-kernel, or sometimes also called anomalous action, is for me just a group homomorphism from G to the outer automorphisms of A. So the outer automorphism group is just the star automorphisms modulo the inner automorphisms, so the ones that are represented by conjugation by unitary, right? So this is the outer automorphisms. Notice that some authors would demand G-kernels to be injective, and I'm not doing that here. For me, this is a G-kernel is just a group homomorphism like this. And then there's a second notion of that's closely related to this one of a relaxed version of this. And these are the so-called cocycle actions. And so what's a cocycle action? It consists of a map alpha from that the idea is that U measures the defect of alpha being a homomorphism. Right, so if I compose alpha G with alpha H, I don't get alpha GH on the nose, but I get alpha GH composed with the adjoint action by this unitary here. So, and then there's a second condition, which is this one here, and it's probably not at all clear where this comes from. It's actually quite easy to get this. So if you look at associativity, right, then you get two ways of putting brackets around alpha G, alpha H, alpha K, namely this one and this one here. And if you work out what this is in terms of alpha G, H, K, then you get this expression for one side inside the AT. You get this expression for the other side inside the AT. And for a cocycle action, you demand this to be true on the nose. So that's where this condition comes from. So I will call this an associativity constraint in the following, because that's essentially its origin. Okay, so how are these two notions related? Well, you can try to take a G-kernel and try to lift that to a cocycle action. And because the map from the automorphisms to the outer automorphism is surjective, you can certainly find a map from G to the automorphisms of A that lifts alpha bar here. And you know that alpha bar is a group homomorphism. Therefore, you know that these two sides here, if you just look at alpha G composed with alpha H and alpha GH, they are equal up to conjugation by a unitary, right? Because you've modeled out the inner automorphisms. And then the only thing that's missing here is this associativity constraint, right? So for UGH, this associativity constraint in general does not hold. So, but it does hold up to an element in the center of the unitary group, right? So that's something that you can check, that this is true if you plug in an additional map from an additional factor, omega GHK, depending on the three group elements with values in the center of the unitary. And since this came from associativity, it's not too surprising that the omega GHK here actually satisfies a cocycle condition. So you get from all of this, for each G-kernel, you get this map omega from the product of three copies of G to, this should be the center of the unitary group. And it turns out this is a cocycle representing an element in the third group cohomology with coefficients in this group here. And then there's a little lemma that you can prove that this does not depend on your choice of unitaries that you've made earlier. And this class here vanishes if and only if the alpha bar lifts to a cocycle action. That's actually not hard to see, because if this omega is actually a coboundary, then I can use the coboundary to modify the unitary so that this constraint here holds on the nose. Okay, so, and I will call this the lifting obstruction here. So that's this name. Okay, there is another invariant. Oh yeah, so I wanted to mention that, so why should I study these and not just group actions? One reason is that these have been incredibly successful for Neumann algebras instead of C-star algebras. So in particular, if you take the hyperfinite 2-1 factor as your algebra and take a discrete and amenable group, then this obstruction that you can associate to a G-kernel is actually a complete invariant for injective G-kernels up to conjugacy. And there's also a realization result, namely that if I pick any element in this group, there is an injective G-kernel that somehow has this as its obstruction. So there, for Neumann algebras, this played a big role in the classification of group actions, for example, on the hyperfinite 2-1 factor. And so you might wonder, so what about C-star algebras in general? What about, for example, nuclear C-star algebras? Can you say anything there? And there, everything gets much more complicated. And so Samuel Ebbington and Sergio Giron Pacheco have a few results there. And if you look at C-star algebras in the nuclear setting that somehow play the role of the hyperfinite 2-1 factor, one of them is this so-called Jiangsu algebra Z. This is what's called a strongly self-absorbing C-star algebra, meaning that it has this nice property that if I take its second tensor power, I don't change the algebra isomorphism. So that is a property that it shares with the hyperfinite 2-1 factor. It also has a trace, which is another property that it shares with the hyperfinite 2-1 factor. So you could ask, are there any interesting G-kernels on this? And it turns out that if you look at G-kernels on this, the lifting obstruction will always be 0, right? So they only come from cocycle actions. And so you might wonder, okay, what about if I just think of the hyperfinite 2-1 factor as the weak closure of a tensor product of matrix algebras? So maybe what about looking at the C-star closure of a tensor product of matrix algebras? You can also study that. And their result, oops, the result that they have there, sorry, is as follows. So this is the tensor product that you can look at. So you take the tensor product of countably many matrix algebras. These are actually classified. So these are UHF algebras. They're classified by what's called supernatural numbers. A supernatural number is like a natural number, except that you allow prime factors to have like infinite multiplicity in them. And they get this divisibility result that if you take the order of this obstruction class for a G-kernel on here for a finite group, then this has to divide this supernatural number that classifies this UHF algebra, this product here. So everything, so whereas here in the setting of von Neumann algebras, there were no obstructions to realize Okay, so I want to introduce one more lifting obstruction that was found by Izumi. And this is in the following setting. So if you have a unital C-star algebra, and we assume that the unitary group is connected and that the center of the unitary group is just the circle group T, then I can look at, I also want that the fundamental group of the unitary group, this maps to K0 of A. I want this map to be an isomorphism. And this looks quite restrictive. Actually, a lot of the examples that we have in mind satisfy both of these conditions here. So for example, this Jiangsu algebra does, the Kunz algebras ON do, including the Kunz algebra O infinity. these infinite tensor products, these UHF algebras do, UHF algebras tensor O infinity do. So there's lots of examples that satisfy these conditions here. Then if you have that, you can construct a group that is an extension of the K0 group of the C-star algebra. And you do that by looking at continuous paths from the unit interval into the unitary group, where you demand that at one end you have the identity, at the other end you end up in the circle. And then you take this and you mod out. So if I forget about the 0 here, then this is just the group of continuous paths in the unitary group of the algebra that start and end at 1. And then this little 0 here means take the identity component of that. And if you mod out by this, then you get a group. And Izumi has proved that this fits into a short exact sequence like this, where if I evaluate my path at 1, I get an element in the circle. And then the kernel of that map is just K0 of A because of this second condition.
May I interrupt for a second? The canonical map from pi 1 of UA to K0 of A, can you say easily what it is?
Yes, so this is using, so I have a map from here to K1 of SA, and then I use spot periodicity. Right. I mean, this is given by a loop in the unitary group starting and ending at 1, so that I can interpret as a K1 element for here, and then I use spot periodicity.
Okay, thank you.
Okay. Right. So the only thing that's sort of that I demand here is that this is already an isomorphism, and I don't have to go to stabilizations, to matrix stabilizations. That's what I'm demanding for this to be an isomorphism. All right, so I have this extension of K theory, of this K0 group. So what do I do with this? One thing that I can do is I can start in the same way with a G-kernel and then lift this to an alpha and a U as before. And then since I'm assuming that my unitary group is connected, and I should have written path connected here. I wanted to change that. But it doesn't really matter for U of A with a norm topology, I guess. I can pick a path from the identity to these elements U, G, H that I had before. And then using the same technique as before, I get a cocycle from this. So I just take this constraint here, and this will represent an element. This will represent, this will be a cocycle in the third cohomology of the group, but now with coefficients in this extension group here in K0 hash. And it's a bit hard to tell from this what this is actually an obstruction to, but it contains, it's an extension of the obstruction that we've seen before, right? Because I have this extension here. If I apply the evaluation map at 1 to this cocycle, I get back the previous obstruction. And then it also encodes a construction in an obstruction in with coefficients in K0 of A that Izumi has studied before. So yeah, so these are some of the lifting obstructions that came up in this context. And now I want to understand these in terms of topology, because there's actually a topological construction that was around for years that captures exactly what is going on here. And that's the notion of a crossed module. So these were invented way back by, I think, Whitehead, who studied this in the context of homotopy theory. So what is a crossed module? A crossed module is a triple like this. So I have two topological groups, gamma 0 and gamma 1. And I have a continuous group homomorphism from gamma 1 to gamma 0. In addition, I also have an action of the group gamma 0 on the group gamma 1. And suggestively, I want to denote my elements in gamma 0 by Greek letters like alpha, and the elements in gamma 1 by letters like U and E. And then the two conditions that the action and this map have to satisfy are as follows. So if I act with an element in gamma 0 on an element in gamma 1, and then apply delta to it, then delta intertwines the action of gamma 0 on gamma 1 with the conjugation action in gamma 0. So that's what this first equation says. And then the other thing I can do is I can take delta, apply it to an element in gamma 1, and let that act on an element in gamma 1 again. And I want that to be the conjugation action as well. So these are the two conditions. And all of this together is a topological cross module. And there are some easy examples that one can immediately come up with. So for example, I could just set the gamma 1 equal to the trivial group. And then you can see that the second condition that the gamma 1 there has to be a B.
So is there, so there is a theorem that I think due to Lode that H3, I think it's for discrete groups, that H3 every class is in H3 is represented by a cross module. Is this true in this context?
Can you say that again? You broke off that.
H3.
Yes.
The third cohomology group of a group with coefficients in a module over the group consists of cross modules. There is such an interpretation.
Yeah, I mean, you always
cross modules, yeah. But I don't know if it applies in this context.
I will speak about maps. I mean, yeah, I will. I don't know if so. I don't know about that particular statement, but this H3 invariant here will come up later, and I'm assuming that maybe it's the same idea. But yeah, so I will.
Can I ask something?
Yep.
Yeah, this definition of cross modules somehow reminds me of Dieter-Drinfeld modules for quantum groups. Is there like any precise relation, or is?
God. I think so. I will talk about this. This is more or less also a two-categorical notion, and so everything that's maybe two-categorical looks like it has. I mean, yeah,
it has something, some kind of Drinfeld center construction.
Yeah.
Okay, great, nice.
Yeah, so maybe I will answer that question later, maybe not. But we can have a discussion about that. Yeah.
Okay, thanks.
Okay, so just to give you one more example. So another example is if gamma 1 is a normal subgroup of gamma 0, then, and this is just the inclusion map here, and the action of gamma 0 on gamma 1 is just by conjugation. That is another cross module, right? These are the straightforward examples that you can come up with. Then the nice thing about topological cross modules is that you can now at least define the first group cohomology with coefficients in a cross module. And here's how this works. So you first define a one cocycle on G with values in a cross module to be a pair like this, where alpha is a map to gamma 0, U is a map from G times G to gamma 1, and it has to satisfy the following conditions. And these look very similar to what we had before, right? So alpha G composed with alpha H is delta UGH alpha GH. That means that this delta UGH measures how much this fails to be a homomorphism. And this is exactly the same condition as we had before. And then for completeness, I also put down what it means for two of these cocycles to be cohomologous. You don't have to remember this. It's just, so you should, I mean, this gives you an equivalence relation on the class of one cocycles so that you can define like the first cohomology of the group G with coefficients in this cross module as this quotient here. And there's a major caveat here because if you do this, then what you get out of this is in general not a group. It's just a pointed set. So it is pointed by the trivial cocycle, And without any further assumptions on this cross module G, it doesn't have any further structure, which looks, I mean, really disappointing, right? Why should you study this if it doesn't have any further structure? But I mean, as you can see from these conditions, this is something that comes up very naturally, for example, when studying group actions or cocycle actions. So, and indeed, if you look at a unital C-star algebra, there's a whole zoo of cross modules that you could write down for this. So here's one, which I will denote by GA. For the gamma 0, you take the automorphism group of A. For gamma 1, you take the unitaries. And then you need a map from the unitaries to the automorphisms. Well, you just pick the at map that sends the unitary to, well, the automorphism implemented by it. And you also have a canonical action of out A on UA, right? Because the automorphisms map unitaries to unitaries. And that structure satisfies these two conditions, and therefore it's a cross module. And then if you look at this cohomology set of G with coefficients in this cross module, just from the definition, this is in bijection with the cocycle actions on A up to cocycle conjugacy. So this condition that we had before of being cohomologous directly translates into cocycle conjugacy, which is very nice. There's another cross module that you can look at, which looks very similar. You start with the automorphisms, but instead of the unitary group, you pick the projective unitary group. So you take the unitary group and mod out by its center. Still, this at map still works because the center drops out if I conjugate. And then this cohomology set is in bijection with G-kernels on A. Whoops. Right. So now we can revisit these lifting obstructions that we have seen before. And the first one, you can spot that immediately by just in the following way. So you have a unital C-star algebra, and then there's a cross module associated to that is coming from an abelian group. Then you take the center of the unitary group, and then this is one of those cross modules where the gamma 0 is just the trivial group. So you have the trivial homomorphism here. So this is a cross module. This is the cross module GA from before. This is PGA. And this is an exact sequence of cross modules. And the thing that's still true is if you have an exact sequence of cross modules, it gives rise to a long-ish exact sequence of pointed sets in this way. So this continues all the way down to 0, which is what these 3 dots here are, but it stops at H2 here because there are no higher cohomology groups with coefficients in cross modules. And this only exists here, by the way, because this is one of those abelian cross modules. And for H2 with coefficients in this abelian cross module, you can show that this is actually the third group cohomology with coefficients in the unitary group here. And this last map here, remember that this was G-kernels up to conjugacy, and this is now this. This last map here is exactly the obstruction that we've seen before. Right. So that's how you see the first lifting obstruction. Then there was this other lifting obstruction by Izumi. Can you see that as well? So if you have a unital C-star algebra and UA is connected, you make all the assumptions as before. You look at this extension group. That also is an abelian group, so it fits into this cross module here. And it turns out that if you take the universal cover of the unitary group and go from there all the way down to the projective unitary group, then the kernel of this is actually this group K0 hash, because again of this. And this, again, fits into a short exact sequence of crossed modules, which then gives rise to this exact sequence of pointed sets. Here is, again, the G-kernels up to conjugacy. This is the lifting of the other obstruction that Izumi came up with, the lifting obstruction by Izumi. So you can see this as well. And I should maybe mention what I mean by exact sequence of pointed sets. So each of these has sort of a base point in it. And what that means is if I take the pre-image of the base point here and here, that's the image of this map here. So that's all that means. Yeah.
But you don't know that, I mean, the fibers over different points may be completely different.
Yes, yeah, that's one of the things that I don't know. Yes, yeah. Right. I mean, this is much weaker than having like an exact sequence of abelian groups. That's true. Okay, but nevertheless, you recover the obstructions here. All right. So there's one more lifting obstruction that I wanted to mention, and that is that exists if the algebra has a trace. So I have a unital C-star algebra A with a tracial state. And then I can cook up the special unitary group associated to that trace. And the idea is, what is the special unitary group in the finite dimensional case? Well, it is the group generated by the Lie algebra where you take traceless self-adjoint elements. So you do the same thing here, right? You pick your traceless self-adjoint elements, that's these, and you take the group generated by these, right? So that's this. And that's the special unitary group associated to your choice of trace tau. And it turns out that if you assume that this map here is at least surjective, then, well, the other definition that you could come up with for the special unitary group is, of course, the kernel of the determinant. Does that work here as well? Yes, we have a determinant in this case. That's the de la Harpe scandalis determinant from the connected component of the identity of the unitary group to this quotient here. So this is the induced subgroup. This is the induced map by the trace, and that's the subgroup of the reals here. Then you collapse that, and that's the you have the scandalis de la Harpe scandalis determinant that maps to this, and it's a group homomorphism. And then it turns out that if you assume that this map is surjective, then this special unitary group is actually the kernel of this de la Harpe scandalis determinant. So you can also describe it as the unitaries with determinant 1, if you like. Okay, so why am I telling you all of this? Because there is another short exact sequence, which I have written down here. So if you now assume the same things as before, which made Izumi's invariant work, namely that U of A is connected, that the center is the circle group, that this is an isomorphism, and in addition, we also assume that this map here is injective, then we have the following statements. This special unitary group is simply connected. The universal cover of the unitary group is homeomorphic to the special unitary group times the reals. And we have a short exact sequence like this, where you have the projective unitary group here, the special unitary group here, and the kernel is this group here. So it's e to the 2 pi I, and then you take the induced map by the trace on K0 and take the image. So since we now have this other short exact sequence of groups here, we can ask, does that fit into a sequence of cross modules? And it does. So there is a cross module like this, where you have the special unitary group here, the automorphisms acting on that. And it has then as kernel, of course, this. And this gives rise to another lifting obstruction for G-kernels, which looks like this. Then you can relate the two lifting constructions to one another. And what's helping there is this fact here that the universal cover of the unitary group is homeomorphic to this. So if I just modify this middle cross module slightly by smuggling in times R here, then I have this commutative diagram here, where now all of the vertical maps are isomorphisms. And you can then check, and this is recovers a result by Izumi, that this lifting obstruction that he came up with in this case actually factors through here, right? Because these groups are isomorphic. And it is given by this tracial lifting obstruction in the first component and just 0 in the second. So this also helps you compute these things. Okay, so I mean, this at least convinced me that maybe this cross-module picture for these lifting obstructions is something useful. But there's another benefit that you get from it, namely that it has this relation to category theory. And I think this is what I wanted to discuss next. Yes. So I have to hit you with a little bit of category theory, but it's not too bad. If you start with a cross module, gamma 0, gamma 1, and delta, then there's a topological 2 category that you can associate to this. And it's very easily constructed. It just has a single object that I will denote by star. And then the 1 morphisms are given by gamma 0. And the 2 morphisms are given by this semi-direct product of gamma 0 with gamma 1. Where if I have a pair alpha and u in this group, it represents a 2 morphism from alpha to delta u times alpha here. And since you want a 2 category, you need all kinds of compositions. You need a vertical composition and a horizontal composition. I've depicted what these are. So for example, this vertical composition where you compose 2 of these unitaries is just the multiplication, not unitaries, these elements in gamma 1 is just the multiplication in gamma 1. And the horizontal composition works like this, where you replace, where you don't take the product of u and v, you take u times alpha of v. So this product becomes twisted by this alpha here. And this whole structure gives you a 2 category. And the thing is, whenever you have a 2 category, you can then go further to topological spaces. So there's a classifying space for a 2 category. There's actually more than one way of defining the classifying space for a 2 category. And the one that I will discuss comes from the so-called Duskin nerve. So the way all of these work is you first construct a simplicial space from your 2 category, and then you take the geometric realization, and that gives you the topological space. And the space that you look at, the spaces that you look at are defined as follows. So the nth level of this Duskin nerve is just given by the pseudo functors of this form here. So what's the n? The n is a 1 category where I just look at the numbers from 1 to n. And then I have a unique morphism between k and l if k is less than or equal to l. So that's this category.
From 0 to n or from 1 to n?
That's from 0 to n. Yes, thank you. That's important. Yes, from 0 to n. Right, but yes, the rest was okay. And then I have this 2 category associated to this cross module. And so what's a pseudo functor? A pseudo functor, usually you want a functor to preserve composition. But now you end up with values in a 2 category. So you can relax that and say, oh, I want my composition only to be preserved up to my composition of 1 morphisms. I only want that to be preserved up to consistent 2 morphisms. And that's what a pseudo functor is. And if that is all a bit much, then I just put down like what the first few spaces look like, right? So the 0th space is just a point. The 1 space is just gamma 0, so the space of 1 morphisms. And then the second space that you get consists of triangles of this form, right? Where you have 1 morphisms like this. And notice that this u in the middle here should be a 2 morphism between the composition of those 2 and this one here. And then for n equal to 3 here, you would get a tetrahedron like this, and the faces would be triangles like this. And from the tetrahedron, you would get a condition about the composition of these 2 morphisms. And then the higher spaces are essentially determined by what happens on the tetrahedra. So this space is co-skeletal in that sense. So, and then you get a simplicial space from this, you can take the geometric realization of that, and you end up with the classifying space. And then what happens is that if I have a one cocycle on G with values in the cross module, this gives rise to a pseudo-functor from G, considered as a one category, where G are just the morphisms, to this topological two category from this cross module. And then if I apply the Duskin nerve to both sides and take the geometric realization, I end up with a continuous map like this. And notice if I take the Duskin nerve of this one category associated to G, this just happens to be the ordinary classifying space of the group, so there's nothing fancy happening. Right. And so what we showed in our draft is that actually you get a well-defined natural transformation of pointed sets where you map the cohomology set H1 G with coefficients in G to this homotopy set, this set of homotopy classes of maps from BG to this classifying space of the cross module. And we're definitely not the first ones to find this. I mean, this is very well known, I guess, to people working in two categories. But what you can then do is you can map these cohomology sets that you get from the lifting obstructions. You can map these to homotopy sets like this. And instead of studying this first sequence, you could try to first study the second sequence and then hope that these maps are good enough to tell you something about what's going on. And there's a few caveats that I wanted to spell out. So we've seen that this is an exact sequence of pointed sets. There's a priori no reason why this should hold for this set, right? So this procedure doesn't give you anything about exactness here. And the other thing is, if you have seen group cohomology, if you take the group cohomology with integer coefficients, you might know that this is the same as homotopy classes of maps from BG to BZ here. So you might wonder, I mean, doesn't that mean that all of these vertical maps are bijections? And that's not true, because this relation here is no longer true for cross-module coefficients. But still, you might hope that these maps are good enough to tell you something about this situation up here. And I wanted to point out that this is actually not too bad, at least in the case where D is a strongly self-absorbing C-star algebra, and so with K1 vanishing. So then if I have a cocycle action of the group on the strongly self-absorbing C-star algebra, there's a way of making or cooking up from this cocycle action an honest action at the price of going to the stabilization. By the way, this is nothing special about being strongly self-absorbing here. This also works for just the general unital C-star algebras. This is also not that difficult. This is sometimes called the Packer-Rayburn stabilization trick. I've seen that in the literature. So what happens here is you just have to pick the right unitary here, depending on UG and alpha G, to make this work. And then you have an action on this algebra here. And since if you start with a strongly self-absorbing C-star algebra, then what you get from this cocycle action will end up in the identity component of the automorphism group. So, and then you can, from this, you can associate a principal automorphism bundle to this action. So you get this principal bundle over the space BG that looks like this. And the structure group here is the identity component of the automorphisms. And there's a result by Izumi based on deep results by Meyer and Gabe and Szabo, that if you have a strongly self-absorbing Kirchberg algebra, and G is a countable, discrete, and amenable group, and BG has a finite CW complex model, then actually the outer cocycle actions of G on D up to cocycle conjugacy are an bijection with the homotopy set that classifies bundles of this type, right? So with the homotopy classes of maps from BG to B out 0D tensor K. All right, and so that is closely related to maps like this one for Right, so why is this good? Why is this right-hand side better than the left-hand side here? Well, for strongly self-absorbing algebras, we can actually compute this right-hand side. And that's a result that I obtained with Marius Badelat some time ago, that if you have a strongly self-absorbing C-star algebra as above, this here, this homotopy set, which a priori doesn't have any extra structure, actually has extra structure in this case, namely it is actually a group with respect to the fiber-wise tensor product. And if you don't have, like if D wasn't picked too small, if D is not the complex numbers, then actually this group here is isomorphic to a group that came up in algebraic topology, in homotopy theory. And just briefly, so what happens is if I have a strongly self-absorbing C-star algebra, there's a symmetric ring spectrum that I can associate to it, KUD. And then this is sort of the space of special units of this ring spectrum. And then its classifying space will give you this. So the thing is that this is something that I can compute using algebraic topology. Okay, and now, of course, I mean, the conjecture is that actually this is what's happening with this map here, right? If I have H1 of G with coefficients in GD, I have this map to this homotopy set here. And the conjecture is that actually this classifying space that you have here is nothing but the classifying space of the identity component of the automorphism. And then, of course, this map here that you get from going here and then using this weak equivalence, that map should correspond to this process of associating the principal bundle to this cocycle action, or to this action, I guess. And moreover, my conjecture is that if I have if I look at any of these cross modules and take their classifying spaces and start with something that is strongly self-absorbing, all of these should be infinite loop spaces. I mean, this is true. If this is true, then you see that this will be an infinite loop space because this is, or I mean, after checking that everything is compatible with the tensor product. But my conjecture is that this is also true for the others here. And I can show this, or at least I have a way of showing this, up to one annoying technical detail that has to do with the fact that for classifying spaces, there's more than one model of the classifying space of the two category. And if the two category is discrete, if you don't have a topology around, these have to be shown to be equivalent. But here, I mean, everything carries a topology, so I have to be a bit careful about results like this. So if I have that these two constructions of classifying space that I can use for this two category agree for these topological two categories, then I get this result here. Right. Okay, but this works quite well, right? This gives you topological invariants then for these G-kernels that you can actually compute using algebraic topology. And one key ingredient here was that we went to this world of principal bundles here. And together with my PhD student, Valerio Bianchi, I'm looking at a slightly different angle on the same problem. So here's another setup. So let's assume that you have a finite group G, and let H be a countable discrete group. And let's assume that we have an action of the product on D tensor K, where D is again a strongly self-absorbing C-star algebra. Then I can cook up an equivariant principal bundle by just neglecting the G here and just using the H action, right? So I take the universal bundle for G times H, but I'm only associating this algebra using the H and not the G. And then everything inside, even this quotient here, carries a G action. And so you get an equivariant principal G bundle over this classifying space here. And bundles like this have a classification in terms of equivariant stable homotopy theory. So you get this homotopy set here. So now you might wonder, right? So if I have a strongly self-absorbing C-star algebra, this was an infinite loop space, right? So if I now have a G action floating around everywhere, does this work equivariantly? And this is essentially the question that we looked at. And since equivariant stable homotopy theory is quite difficult, we just picked a setting that was easy to deal with. So we picked a very easy to handle group. We just picked Z mod PZ for a prime P, because that also doesn't have that many subgroups. So you can easily deal with that. And then we picked a finite dimensional unitary G representation and looked at the C-star algebra that you get from taking the endomorphisms and taking the infinite tensor power. So that's a UHF algebra on which this G acts now on each tensor factor. And notice that I'm not taking the equivariant endomorphisms here, I'm just taking all of the endomorphisms. And then I have the compact operators as well, and these also need a group action. And there I just pick all of the representations of G with infinite multiplicity. So I pick the compact operators on a full G universe. And then what we can show is that actually this morphisms here, this is now a G space, right? Because G is acting on everything inside. It's actually a G equivariant infinite loop space. So you get an equivariant cohomology theory associated to it, just as in the non-equivariant setting, which we denote by this. And actually, we can identify this again with something from algebraic topology. And the setting is, or the result is very similar to what we obtained in the non-equivariant case. So you get kind of the equivariant units here. So that's this cohomology theory here on the right-hand side. And then if you pick since this is an equivariant cohomology theory, I can, it's indexed by like a degree, but also by subgroups of this group here. And if I pick G as a subgroup of itself, then I get this set here.
Well, may I interrupt you? So first of all, I think you used a British understatement when you said that G C mod PC doesn't have that many subgroups because it has two. What is the meaning of G equivariant infinite loop space? Is an infinite loop space with a G action, or is it something else?
So it's essentially the so what we look at is G equivariant spectra, right? And then the infinite loop space is if you have a G equivariant omega spectrum, then sort of the first space would be what I call a G equivariant infinite loop space. So the idea is that this is actually this is part of a naive G spectrum. So it's the first space in a spectrum, and the spectrum that we get is actually an omega spectrum. And it's a naive G spectrum.
Okay.
Right. That's also my final slide. So this is actually the end of the talk. So thank you very much for listening.
Okay. Thank you very much for your talk. Do we have any questions from the audience? See.
Yeah, I have a question. Yeah. It's about the conjecture before the last part. You said that you could prove the conjecture up to the comparison of these models of the classifying space. So I mean, like, you use this dust to construct the classifying space. Previously, you used this dusting nerve.
Yeah.
But you can prove the conjecture using another model instead of the dusting nerve. Is that right? Okay.
Yeah, that's correct. Yeah. So
can you say, like, in a few words? Can you say in a few words where the difference, like the apparent difference between these models lie?
Yes, I can try. So, right. So essentially, how the second way of constructing, I mean, yeah, so another way of viewing the cross module for this is you get you get this groupoid, right? So where you have that your objects are the automorphisms, and the morphisms are this product, and these two maps. One of them is the projection onto the first factor, and the other one is just taking the adjoint of U and multiplying it with the automorphism. And this is a one category, and you can also view the two categories. Since it only has one object, you can view this as a monoidal one category, right? So, and this is the one category, and the monoidal structure comes from the fact that I can now compose. This is again a group, and I can compose again, right? So, but then what you can do is you can take the classifying space essentially in two directions. I can first take the classifying space in sort of in the UA direction, and that at the end of the day will give me something like EUA cross adjoint out of A or something like this. And you can, if you pick the right model for EUA, then this will become a group by itself. So you can take the classifying space of that. That would be the second model of classifying space. And it turns out that this here, it's not too hard to show that this is actually the same as out 0 of A tensor. Okay, and I should have written D instead of A here. My apologies, I switched.
I see. Okay.
So and then you get, and the group structures agrees. There's a group homomorphism that is homotopy equivalence, and then you get this. So I know that this works. I know that, but I don't know if this way of getting the classifying space is the same as the one that I get from the Duskin. And that's exactly the thing that is proven in case of discrete two categories. So there are papers about discrete two categories that show that actually it doesn't matter whether we take the Duskin nerve or this double nerve construction that gives you this here.
I see. Okay, so any like conditions on the
can I ask a question?
Sure.
Yes. Yeah, I'm sorry if my question is elementary, but I observed that you make a correction in your talk at the first part of your talk, and you correct connected unitary group to path connected unitary group.
Oh,
so
right, yes.
So I wonder if there are some algebra for which the unitary group is connected but not path connected.
I mean, so the unitary group is a Banach-Lie group with respect to the norm topology. And if I have my point set topology correct.
What topology you are considering on the unitary group? The usual topology?
Yeah, this is just, I mean, I consider my algebras to be unital. So there's the unitary group only has like the norm topology is the interesting one. If I take a non-unital algebra, if I take the multiplier algebra of A tensor K, for example, then I would have like several other topologies to consider. But here I just take the norm topology.
Yes, I see. Thank you. May I ask another question? According to the definition of a morphism from pi1 of unitary group to K0 of A, you constructed a morphism. So one can construct this a similar morphism from pi2 of u of a to k0 of a. So according to the Bott periodicity, can one say that this is an isomorphism for any algebra? One can define a morphism from pi2 of unitary group A to maybe k0 of A or k1 of A. Is it the case? And am I mistaken to think that it's somehow an isomorphism for every algebra?
No, you can, well, using this, you could construct a map from pi2 u of A to k1 of A, but we run into the same problem that you had before, right? So this here is in general not an isomorphism, but I mean, for general C-star algebras, what happens is that, I mean that's always, the problem is always that to get the right homotopy type for the unitary group, you would have to go to like infinite matrices or something, right? So for example, this here would be your K1. And right, you need to stabilize.
Yeah. I mean, you can define pi kn of A as pi n minus 1 of DCUM infinity. So
Yeah.
it's a problem of stability. I think so. For Hilbert algebras, is that an isomorphism? Does it stabilize it at 1?
For which algebras?
Kirchberg.
Kirchberg, yes. For Kirchberg algebras, this is true. I think this is true for
which algebra? Which algebra?
For Kirchberg algebra.
The simple purely infinite nuclear unit sister algebras. Kirchberg algebras.
Kirchberg,
yes.
Those are classified by the Phillips-Kirchberg theorem.
So is this condition on the relation between the homotopy groups and the K theory related to the UCT, I guess, right? Or no? Okay.
You mean this one?
Yeah, for example.
I mean, this is
stable rank kind of thing.
Yeah, I don't really know what the UCT is, so yeah.
I mean, the UCT usually helps you compute like KK theory groups from the K theory groups. So
yes,
okay.
Thank you very much.
No worries.
Okay.
I think, I mean, this should be true that this is an isomorphism. This should not only be true for Kirchberg algebras. I think this is true for classifiable algebras or for Z-absorbing.
Oh, really?
Yeah. So there's lots of examples that have this, but at least in the classification program. But
okay, so
thank you.
Okay, I have a meta question. So you started with a problem, a lifting problem, right? Classifying problem of actions, of outer actions of a group, when they can be lifted, when they cannot, and said that in a particular case, for von Neumann, 2 factors, I think it was, that there is an abstraction that completely classifies these actions. How so? And well, you wanted to do to study the same question in the C-star setting, and then, well, the research led you to other things. But how far, I mean, are you from this original program you said about solving?
oh yeah, so yeah, that's a good question. I mean, if you want me to go back to the end.
I mean, the first slides show that somehow you needed a finite invariant, and you somehow constructed one. But then I would expect you to say, I would have expected you to hear that maybe for some classes of algebras, this is no invariant classifies.
Yeah, so I mean, the classification result that we have so far is really this one, right? So where you have the outer cocycle actions of G on a strongly self-absorbing Kirchberg algebra, that this gives you this, right? And now we try to improve essentially on that. So, and that is related, as I said, to like working out how good are like these maps here in detecting. Like, I mean, this is telling you that, so to translate that, right? This map here from this would be the cohomology set classifying all cocycle actions of G on D, and this is the thing that is in bijections with the outer one. So this map here should be surjective, right? That's what you get from this, which is also telling you that if you want to study outer cocycle actions, if you want to study cocycle actions on your algebra, then as a first step, it's probably good to look at these invariants here. Yeah, so, and I mean, then this was more, I was more interested in like the interplay between like the various lifting obstructions that you can get for these G-kernels here, right? So now if you want to really do the classification, then you need to go back to questions like this one for other strongly self-absorbing C-star algebras. I don't know. I mean, if I can show that, I mean, if this last part is true here, that these are infinite loop spaces, then my hope is that one can somehow get results like this for more general, strongly self-absorbing C-star algebras, for example. Without, it's handling these without the group structure around is incredibly hard, right? Because it's just a pointed set, so there's very little structure there to understand that. This is much better in that sense because it is a group in the sense of, for strongly self-absorbing algebras. So there you have a chance of understanding something. I mean, as you said, I mean, when you have only an exact sequence of pointed set, that's not much structure. it's very little.
Yes. And yes.
What can you say about G-kernels for Kunz algebras specifically?
Oh, G-kernels for Kunz algebras. Oh yeah, that's another. So the Kunz algebras would absorb O infinity, right? So one idea would be, well, since you can tensor with O infinity without changing the algebra, so you can ask the classification that, I mean, that this, for example, gives you for O infinity is strongly self-absorbing and Kirchberg. So you have this result here, which gives you this classification by bundles. So you could ask, what happens if I take now the set for O infinity, for On here instead of O infinity, and let the set that I get for O infinity act on that? Can I somehow describe the orbits and these things? I, at one point, had a look at questions like this, but it's still incredibly hard to find good answers. So there's nothing that I can say at the moment about this, but that would be my approach. That would be my idea. I don't know.
Is there some indication that or some concrete example of something?
I mean, of course, that's a different question. If you can construct like example actions on On or on O infinity. I have not thought about that. Other people have, I think. So there are nice examples of actions, group actions on On and O infinity, but I don't know too much about those. So if I start talking about those, I will mess it up.
Okay.
One thing. So I I mean, I don't know about the things, but I heard people talk about cross modules. They regard this as a model for scale for spaces. Well, a simplicial set that is determined by its two skeleton.
Yes, yeah.
But here you, I mean, the difficulty is that you do not just have a simplicial set, but a simplicial space.
Yeah, yeah.
And yeah, so that's why the multiplicity of models shows up. I see.
Yeah, yeah.
Yeah. By the way, this comment I made about the relation between H3 and cross modules, I put in the chat.
Oh yeah, I was wondering what that was. Yes.
Yeah, so this is in Laude's book on cyclic homology in his appendix C.
Right, okay.
But I think this goes back to an old paper by Laude. That's why he included it in his book. You might want to have a look at the
right. Yes.
But I don't know. I mean, maybe there is I mean, somebody has studied whether this is true also for topological groups and topological and simplicial spaces. Maybe, I don't know.
The way I see this is a bit like, I mean, there's whenever so if you pick two, I don't know, for example, Lie groups, and you look at the group homomorphisms between G and H, you can take those and map them to the homotopy set of homotopy classes from maps from BG to BH. And the way I think about these problems is essentially like that, right? How much of the information about the homomorphisms is actually captured by the maps between the classifying spaces? And these are like old questions that have been studied, for example, by, I think Sullivan has studied this for Lie groups, I think. But this is much more complicated. I don't have Lie groups. I have these strange automorphism groups. And the unitary group, at least, is a Banach Lie group. That's not too bad. But yeah, the automorphism group is quite ugly from the point of view of group theory. So the techniques that they use probably don't work in this context anymore. But nevertheless, I wanted to have a look at the papers at the techniques that they have used. If something of this type can still be used for these problems here.
Okay, so if there aren't any further questions, I will stop the recording.